Hey guys, so in the previous video we left off with finishing the methyl and primary substituent thought process. So now we got to just finish out secondary and tertiary, right? Now I finished writing in the primary, we'd get second SN2 or E2. E2 is if you have the bulky base. SN2 it would have been literally anything else. So if you had H2O, OCH3 minus, Cl minus, doesn't really matter. Okay. So now secondary. So a secondary leading group would be something like this, right? Think of the carbocations. We know a secondary carbocation is this. So just replace the plus charge with the leading group. All right. So how do we decide now what of the four we're going to do, right? So in this case, we can't really rule out anything. All right. Secondary is going to be the hardest one to decide. Methyl is the easiest because it's always SN2. Primary, it's almost always SN2 unless you have a bulky base. Tertiary is going to be the next easiest. Secondary is the hardest because we can't really rule out any of the four by substitution alone. Okay, why is that? Well, a secondary carbocation is relatively stable, so we can't rule out E1 and SN1, right? So we have to look at all four. So if we can't figure it out through the substitution, we can't really focus on our substrate. We really have to look at what we're reacting with, right? So I have this secondary alkyl halide, okay? We can't figure out anything from this. So you have to look at what you're reacting with. So what I would ask myself now is, do you have a good nucleophile or a strong base? Okay, good nucleophile or strong base? Or strong base. All right. So what fulfills any of those requirements? Remember, it says or, not and. So a good nucleophile, usually something with negative charge, so like Cl minus. Cl minus is a good nucleophile. It's not a good base, but remember, it says or strong base. So we covered the one requirement necessary. We only need one of them. It could be both. It doesn't matter, but at least one. Okay, cool. How about OCH3 minus? Well, we know that that could be a good nucleophile, but it's also a good base. We know that we've seen something very similar to OCH3, which is just OH minus. We know that is a good base and it's a good nucleophile, right? So we could put here OH minus too, right? How about something like CN minus? Well, you haven't been exposed to that as much, but you will later on. You'll understand that it's a good nucleophile, but it's a bad base, right? But as long as you covered any of the criteria, we can say yes. Okay. So I'm just gonna move this over. So let's see. So I wrote yes. I have that. All right. So here's where it really comes into play, that nucleophile and basicity video, okay? SN2 and SN1 reactions, they prefer that you have a good nucleophile, or not a good nucleophile, but they rely on the nucleophilic character. Elimination reactions are acid-base reactions because the base takes a proton, so it focuses more on the basic character, all right? So now, let's look at our substitution one more time. We talked about how SN2 is going to be limited by steric hindrance, right? That's why primary is relatively quick with an SN2. We don't have that much steric hindrance. Methyl is really good. But what about secondary? Well, if you look right here, I have this methyl and a methyl. That's two more substituents, right? So we have a little bit more steric hindrance now. So SN2 is going to be limited even more, right? So how do we decide if we're doing SN2 at all? If we're limiting it as it is, right? Well, SN2 would require, remember, substitution reaction, requires a nucleophilic character. And it needs to be strong enough to kick it out in one step. Usually that's a strong nucleophile, right? If you have a lot of electrons, it's good. It'll be fine with reacting to kick it out instantly. If you're weak, it's going to be a little bit harder because it's fine staying the way it is, right? So the only way you can get an SN2 on a secondary leaving group, right, is if your nucleophile is not a good base, all right? If your nucleophile is not a good base, so something like Cl minus, Br minus, I minus, they're good nucleophiles, bad bases, you can get an SN2. So erasing everything here, writing only Cl minus, we can get SN2. Comes in, kicks the Br out. That works. What about if I had a good nucleophile but a strong base? All right, so think about it. We have a secondary substrate. SN2 is hindered as it is. Now you're increasing the basicity of your compound, your reactant, your right here, this whatever you have put over the arrow, right? So SN2 already is not good at it. It's slow. It'll happen, but it's slow, versus like a primary or methyl, right? So it's already limited as it is. But if you don't have if your good nucleophile is not basic, it can happen. But now I'm increasing the ability of our nucleophile to also be basic. So SN2 sucks as it is. Not sucks, but just slow. And now I'm adding the other factor, another factor on top of it that makes it even more basic. Basic character favors E1 and E2. So now I'm already leaning even more to the elimination reactions. So if you have a good nucleophile and it's a weak base, you can get SN2 on a secondary carbon. If you have a good nucleophile, but it is a good base, so something like OCH3 minus, OH minus, something like that, right? You are going to get E2, not SN2. So instead, what would happen is we'd grab an H. This would come down, kick the Br out, and now we'll get this product, the elimination product, right? So you can see here now that how the factors come into play regarding these different reagents, okay? So if you think critically, you'll be able to understand it. And of course, the practice is where it's going to really stick, all right? So SN2 happens on a secondary if you have a good nucleophile and a weak base. Now, comparing the speed of SN2 on a secondary versus primary, it's going to be much slower on secondary as it is because of the steric hindrance, okay? So keep that in mind also. All right, so we've established we can get, so if we say yes to this condition here, the next question we should ask ourselves, and I'm just going to move this kind of out of here. Next question we should ask ourselves is the nucleophile basic? And remember, is the nucleophile basic? Or, yeah, basic. When I say basic, it means like strong base. If I say no, right, so I'm going to go answer no, we're going to get SN2, no. And it's going to be slower than it would be on a primary. If you answer yes, we get E2. So, yes, E2. Okay? So, we've covered the SN2, we've covered the E2. But that was on the condition that I had a good nucleophile or a strong base. Well, what if I answered no to that question? What would be an example of answering no to this question based on what's attacking? Well, it can't be a good nucleophile, can't be a strong base. So something like H2O, CH3OH, right? Stuff like this. When you don't have a charge, not a good nucleophile, and you're not a strong base either, right? So in this case, we now have to consider what's going to happen here. We have a secondary substrate, right? So think of the carbocation reaction. Secondary carbocations are relatively stable. So the possibility that the carbocation can form is pretty good, right? So what would happen is we would get the substrate would actually leave because these weak nucleophiles and weak bases are not strong enough to directly kick out the substrate. So the substrate, so the leaving group. So this leaving group has to leave on its own instead, giving us a carbocation. Okay. So you can see here now that if we didn't have a strong nucleophile or a strong base, right? Well, then we can have the possibility that we can get a carbocation. All right. And so, how now do we decide? Is it going to be SN1 or is it going to be E1, right? Well, SN1 and E1 are strongly related to each other in terms of it's hard to isolate one or the other, right? Now, just keep in mind, carbocation, so it can rearrange. Right? That'll happen before your nucleophile or base does its thing, okay? So we are going to have a carbocation, and now you got to think, okay, well, SN1 or E1, what's it going to be? So one thing that I didn't mention before, elimination reactions are more favored if you have heat. All right. So if I had this right here, Br, H2O, we've established that it could be a carbocation. All right. Leaving this as it is right now, we'd have a carbocation here. And this H2O can attack. All right. And we'd get the OH on there, so the SN1 product. If I wrote heat, which oftentimes you'll see it as this delta symbol, right? That will favor the elimination reaction a little more. So because it's weak, remember, we're going to get the carbocation, and then this will grab the H, giving us this. Okay? So if we answer no to this, no, it's not a good nucleophile or a strong base, right? So then we're going to say, okay, well, heat. No, it's dead or white. Heat added. Well, we said yes. If we say yes, because we had heat, more favors elimination a little better. To get E1. No. Okay, well, then we'd favor SN1 a little bit more. But again, you could get a slight mixture of products, and usually if that happens, they will hint it on the test that there's a mixture. All right? And so remember also, if you get the carbocation, rearrangements can happen. All right? Don't forget about that. So also, it says the requirement was a good nucleophile or a strong base. What would be an example of something that is not, because I said either one of those would fulfill the requirement. So a good nucleophile that's not a strong base would be something like the halogens, like Cl minus, Br minus, I minus. How about a good base, bad nucleophile? Something like terpbutoxide, right? Terpbutoxide is a bad nucleophile, right? But it meets the criteria that it's a strong base. It's got that O minus. So we'd say yes, and then it's asking, is a nucleophile basic? Right, we said that it's basic. So E2 again. All right. So that covers the secondary. All right. How about tertiary, the last one? Now again, this is not a chart, a know-all, do-all. This is not something like that. All right. You need to get the thought process down. Using a chart is just not going to, it's just not effective. So tertiary now. So this would be a tertiary substrate, right? So we have a lot of substitution on that carbon. So right off the bat, think of SN2. SN2 is limited through steric hindrance. It's harder for it to happen the more hindered the nucleophile is, and the more hindered the substrate is. We said secondary was already pushing it for SN2. Tertiary is just completely, that's not happening, right? So tertiary does not undergo SN2. Two sterically hindered. Doesn't really matter what your nucleophile or your base is. It doesn't really matter. All right. So SN2 can be ruled out. Too bulky. What about a strong base? And so that means the next thing you should be asking yourself, we can cross out SN1, right? So we have SN1, sorry, not SN1, SN2. SN2, E1, E2. So cross out SN2, not happening. Can I eliminate the carbocation reactions E1 and SN1? Well, think of the carbocation that would form when the Br leaves. It's tertiary. That's pretty damn stable, right? Even more stable than secondary. So the possibility that a carbocation reaction can occur is pretty likely, or at least could be a possibility. So you can eliminate SN1 and E1. How about E2? E2 is not bound by the same rules as SN2. We said SN2 is worse when it's sterically hindered. Now E2, just because it has that 2 does not mean that it follows the same rule. In fact, E2 can in fact occur on tertiary. All right? The driving force to determine what that is asking yourself, what do I have a strong base? Right? So, strong base. Remember that these SN2 and E2, we prefer things to be strong. SN1 and E1 are when we don't have strong things in general, right? If we have to obviously look past the substitution. Strong stuff favors SN2 and E2. So strong base, do I have it or not? Right? If you have a strong base, it will favor E2. So I'm going to say yes. All right, then E2. What if I said no? Also, what would be an example of a strong base, right? OH minus, OCH3 minus. Yeah, anything like that, really, right? And it does not matter in this case if it is a good nucleophile. SN2 is not happening here, so the nucleophilic ability on a tertiary carbon doesn't really matter. SN2 is just not happening, right? What really you got to look at is the basicity. That's going to help you determine it. So E2 is going to happen if you have a strong base tertiary. What if you said no, right? Well, now again, it's going to be, that means we have something weak. So H2O, methanol, anything that's really nothing that, if it's not charged. Cl minus, right? Because remember, we're talking about strong base. Cl minus is not a strong base. It's not. And it doesn't matter if it's a good nucleophile in this case, because we're not doing SN2, right? This is solely dependent on the basicity. So Cl minus would be considered a weak base. So I would answer no to that question if they gave me Cl minus, all right? So you see, you got to look at all the factors here, right? You can logically get through these questions. So I said no to this question. I don't have a strong base. So that means I'm eliminating E2, right? Now SN1 and E1, the carbocation reactions. So how do I determine which one? Well, we said it before, right? The idea of heat favoring E1. So kind of ask yourself, heat being applied, right? If your answer is yes, then we'd favor E1. If you answer no, favor SN1. Of course, remember the rearrangements, please. Okay? And so that pretty much covers the thought process you should be going into. Now you'll notice, solvent was not mentioned once in this chart. Not at all. That does not mean it doesn't affect anything here. The reason it's not included here is because its importance is overstated. All right? Solvents can push the reaction in a certain direction. It will not be the thing that decides it. Now, you'll often hear that SN1 and E1 are called solvolysis reactions, right? That's because the solvent is attacking or acting as the base, right? But that's also just because usually we can write that the weak nucleophile or the weak base is just what the solvent looks like. So I said CH3OH was a weak nucleophile and a weak base. it's also a solvent, methanol. It's used in certain things. So is H2O. So that's why it's called solvolysis, because it can also attack, right? But that doesn't mean that it's strong or anything. Okay, so like I said, so do not get too caught up in a solvent question if they give you solvent. All right, it does come into a play when you're thinking if you have multiple substituents, multiple leaving groups on your molecule, and they'll say, okay, you have multiple leaving groups reacting with OH minus under some random solvent, right? And you got to think, okay, well, you got to determine if they're SN1, SN2, E1, E2, and then the solvent can now affect whether or not one would go more SN2 or kind of remain the same. And there is an example question that I'm thinking of in my head. I'm not going to show it here. I want to show more simpler examples first, and we will ramp it up. All right? But do not get too caught up in the solvent. Another way they can bring solvent into this is they'll give you 3 nucleophiles or bases, and they'll say arrange these in terms of increasing nucleophilicity in apolar aprotic solvent, like DMSO. Okay? That's how they love to show these things. I will give you tons of example problems. All right? You'll see tons of them in workshop, your past exams. All right? Make sure to ask questions on this topic. If you have a question, ask it. Do not keep it to yourself. It can only hurt you. This is a very difficult topic to grasp originally. I struggled with it in the beginning. All right, but I started logically thinking it through, rather than use these charts. The chart doesn't really help when they give you like one of those mug buster questions. Even this chart, I would not rely on this sort of chart that I wrote. Like I told you, broke down in the previous video if I had a primary carbon with some beta branching, right? Well, SN2 wouldn't happen despite the fact it was primary. Okay. In the next few videos, we're going to be going over a little bit more in depth about some stuff. The next video, primarily, I want to cover some stuff about tert butoxide. I mentioned it was a bad nucleophile, and that it was bulky. So we have one other thing that comes into the play if we have a bulky base. All right, and it's not at all a difficult thing to understand. Just quickly have to introduce it because you definitely will see this. Okay. And so I hope everything here made sense. If it didn't, please feel free to email me or talk to CLC. They'll help you guys. They understand that this is a hard topic. Most people struggle in the beginning, but with practice, you will get it. All right. Now, like I said before, be careful of the charts. Talking about solvent, charts about what solvent is polar aprotic, sure. But again, remember, weird stuff, usually polar aprotic. Polar aprotic, if it sounds weird, like DMSO, DMF, right? Stuff like that. Acetone. Or you could talk about like what's a good nucleophile, what's a good base, bad nucleophile. Like those are that I would consider a relatively good thing to know. But yeah. So like I said, hope everything here made sense. Good luck, with this topic. Of course, more videos will come.